I'm going to talk about encryption, or give an introduction to encryption. What is encryption? Well, it's a means of secretly communicating. It's a means of taking a message and obfuscating it, so you can pass it around in a public setting, like the internet, or put it on a bulletin board somewhere if you're in meet space, and no one can tell what you're saying. Only the intended recipients can tell. It has a long history. I'm going to touch on that as well. And it's absolutely essential for the modern economy, electronic, digital commerce, the internet, the web. And then there's even really cool things that are now popped on the scene, like cryptocurrency. All this is made possible by encryption. I'm going to throw in a caveat that basically cryptography is an absolute arms race, meaning it's adversarial in its nature. There's cryptographic researchers both trying to produce new, more robust cryptographic algorithms to protect messages, and there's also people on the other side trying to come up with ways of breaking these procedures or finding exploits so they can decrypt without anyone knowing what's going on. So there's a constant sort of tension between the people trying to break the encryption and people trying to come up with new encrypted techniques. So that being said, the material I'm presenting is essentially obsolete, but it illustrates key principles that modern cryptography builds on top of. It's just some of the details have changed for modern cryptographic algorithms. First of all, there's some terminology. The plain text is the original message, so that's your email to someone, that's you sending that purchase request to Amazon.com for your 100-pound bag of rice, 200 pounds of beans, and a hockey mask to get you ready for the world today. And includes your credit card number and all that kind of stuff. You don't want other people knowing what you're doing, what you're preparing for. So you want that to be a secret. You don't want them to get your credit card number. You don't want them to see your embarrassing Amazon purchase history. So you want to keep that all under wraps. So that's what the plain text is. That's what you're trying to send, that you're trying to keep secret. Ciphertext is the encrypted version of that message. So this is the obfuscated version of the original message. This is what's safe to be passed around in public. And then the last piece is a key. So a key is some necessary information to be able to encrypt or decrypt that message from ciphertext into plain text or back again. There'll be a couple different keys we'll look at. So some of them are symmetric and some are not, meaning they can be used for both encryption and decryption, or some just work one way. The first, and now I'm going to get into setup for basically the simplest encryption scheme that really everything is sort of based on, at least you can think loosely or sort of in a abstract sense. So let's say we take letters. We order them alphabetically, and we assign a number to each letter. So we have A as 1, B as 2, C as 3, so on and so forth. We've assigned every letter a number. Now, along comes, with that idea in mind, we can use the Caesar Cipher. So who's this guy? Well, this is Gaius Julius Caesar. Well-known historical figure, of course. Some fun facts about him is he devised this cipher technique to obscure messages that he would send off to his allies and generals and so forth. and apparently it worked just fine. Though we'll see how. I think that really was based upon how few people are literate at that time to begin with. So you'd have to have it would be a very small number of people at that time are both literate and thinking like, oh, maybe this is some sort of scrambled message. Anyways, he came up with the Caesar cipher. Oh, fun side note, I always like to throw this out about Julius Caesar. He also had a second, like, kind of secret superpower, just ridiculous, that also kept his information safe, is he possessed what people at the time thought was incredibly unusual, is that he could read quietly, meaning he didn't have to speak aloud as he read. So he didn't have to read like a kindergartner, which apparently everyone else did. Again, I think it's because so few people were literate that they just basically read like kindergartners, just like saying aloud every word as they read it. But he apparently trained himself to read quietly. So that was also, apparently that was the thing. People would like hide outside, your tent, your house or whatever, and be like, oh, he's going to read the message. And then he starts reading aloud, go kill these people or something. And then it's like, okay, well, now that we know the plan. But yeah, that was his way around that. Anyways, that's enough of that. The Caesar cipher is also called a substitution or shift cipher. So again, we have our lexicographical ordering here. Then we're just going to pick some number, say like 3. We'll add it to the number in question. So we'll take the A, make it to a 1, add 3 to it. We get 4. Add 3 to B, we get 5. That gives us a new sort of cipher letter on the other side. Ooh. And then the only sort of edge case or trick to it is, well, the last few here, we need to wrap around to the beginning. So there's this example, send me 100 more soldiers becomes, well, this gobbledygook nonsense. So, to the mind of antiquity, this was a very difficult thing to break. Now, if you want to decrypt, you could just take one of these letters. So you look at D, that's going to be 4. You subtract 3, you get 1. It's A, which corresponds to this. So we can see how you can go back and forth. It's pretty simple. Yeah, so that was, incredible, political and military technology, 2,000 years ago, but now it's kind of meh. But that's what a substitution cipher is. But we're going to build on top of this. What are the problems with this? Oh, first comment is the key in this case for the encryption algorithm is just the offset, so like the +3. The real problem is there's only 25 to try. So if we go beyond that, then it starts the loop around. So we could do, +1 or +7 or +8, and we could only go up to +25. Or we just, because we have that wraparound feature, we just wrap around again. So very easy to brute force. It's not really, that you'd only, I guess, maybe you could fool someone with it today, but it's not really like a reliable means. But we can see we can do much more clever things with it too. So a better substitution cipher would be just to make an arbitrary mapping from one letter to another. So now all A's get replaced with X's, all B's get replaced with Q, so on and so forth. So yeah. So if I wanted to take the person's name, like Abe, for example, I put X, Q, A. And then the decrypt, again, we just have to know what this is. Oh, that was terrible. That's the worst arrow of all time. I say that like every video. But anyways, yeah, we have to just have this mapping. And then we can reverse the mapping and then decrypt. What's the problem with this? Well, it's better in that there's a lot more. There should be, 26 factorial orderings, right? So if we shuffle all the letters again, we get a totally different key. So there's a lot more keys now. The key is just that mapping, right? So it's just, A is mapped to Q or whatever I said. The rest, you just have to keep that around as your key. The big problem here, though, so this seems a lot better. The problem is it's a statistical, you can do the statistical style attack, which is one general way of attacking cryptographic methods in general. So some letters occur more frequently than others, like RST, LNE. So if you're familiar, I guess if you're a boomer or a millennial, then this makes sense to you because this is from Wheel of Fortune. These are the most commonly used letters in the Latin alphabet in English. So, if you map E to X, well, if you see a lot of X's in your ciphertext, you can probably guess, that's probably the E, because E is the most common. So basically you just line all the letters up, sorted by how frequently they generally occur, and then you just take a lot of ciphertext, you compute the statistics on each letter, and then you can probably make an alignment there. The next problem is the sender and the receiver, they must agree upon the key. So this is called this is a symmetric key. So it goes both ways, and they both have to know what it is. Symmetric key. So this is, the sort of the basic means of encrypting something, but it is still used today. We'll see how that can be incorporated later. But that's another problem. And really the biggest problem here is the statistical attack, right? So and that's because once you've fixed on a mapping, E is always going to be X for a given key. Then since there's always that association, it's kind of easy to flip it around and see and kind of guess what the mapping might be, like I was saying. So let's go forward. So that gets us to Enigma. So Enigma, it was the German encryption system, is electromechanical machine, and it was just a substitution cipher. So it would map, well, I guess they got, they're Latin, but I think they might have, maybe they just omitted their little umlauts and whatnot. So how nice. So what they would do is, let's say we have one mapping, E is mapped to X at step 1. When you press a button, so you press a button E, it pop up over here. Let's say, you can't really see, but let's say this is X or something like that. Or, no, it's not going to be there. It's going to be like down here, XYZ. So you press E, this light bulb lights up with X behind it. Right, great. You press, and all the letters are mapped. You press another button. Let's say you just hit E again. Well, these gears here spin, and they are what actually determine the mapping. So as you press a button, it advances the gears. So now if you just hit E again, well, now it's mapped to Q. Now you press E again, it's mapped to A. And so on and so forth. So these gears essentially determined the mapping, the state of them, so how they're configured. And then as you typed throughout the day, as you sent messages, so at the beginning, when you're going to send a message, you'd put the gears in the initial configuration, type out your message, and this would whirl through, millions and millions and millions of different substitutions. And the decrypt, you would just pop this bad boy out, this set of gears, and flip it around. And then you type in the ciphertext, and the plain text will light up here. It's absolutely ingenious device. This one shown has 4 rotors. The standard one had 3. The German Navy, who thought they should be cooler, added in an extra rotor. This particular image is of a Japanese manufactured Enigma machine based upon the German model. It's very cool that they thought of this. Absolutely, to me, it's just incredible when someone sits down, comes up with this in a world, basically pre-computing, or in very, let's say, nascent computing time. Think of this. So it's basically a moving substitution cipher. Let's move on. So what was the problem with it? Again, so the Enigma machine destroys most of the statistical problems with it. You still have this symmetric key issue. So the sender and receiver must share the key beforehand. So what they did is, DOS Germans would have the book of codes, and on it it'd be like 331. We're going to use this this configuration of the gears. So they made sure to guard this book very carefully. Basically the officers in charge of operating the Enigma machine, they're under super strict orders. If your position is being overrun, you burn this book no matter what. The clever Deutsch would they also wrote the code book for the German Navy with water-soluble ink. So if the ship went down, the book would be erased, almost guaranteed. So a little cleverness. But this man over here, Alan Turing, which I'm going to cover a lot more later, he was able to he built a system called the bomb, which essentially was multiple Enigma machines connected up together, and he would basically was able to sort of brute force the settings back, and also with some combination of the Germans also got lazy and would set wouldn't always change the rotor settings every day too, so they would do that. So his whole thing was basically he would use his system to crack what the initial settings were for the Enigma for the day. Then they could read everything they were saying. But then also the Germans got sloppy too, and there's a bunch of other little things there. So yeah, he's pretty awesome. He really caused them a lot of grief. It took them a while to catch on. Even I don't think they really did. It ended up being towards the end of the war. They just said, "Oh, whatever. We won't even pretend to hide that we're cracking their messages." But anyways, Turing's awesome. I'll cover him some more in another history lecture on this. But yeah, it's based upon the fact they had this code book, the shared key. He came up with a way based upon the design of the Enigma that basically reverse engineer what the settings would be for the day. Pretty cool. So now let's talk about another thing. The one-time pad. So this is a pretty slick system. It again is in the sense it's almost like substitution for binary. It uses exclusive OR. So if this is the plain text over on this side, and this is not the cipher. This is our key right here. If we do XOR with this sort of parallel bit pattern, we'll get out a ciphertext which basically has no correspondence with the input. It's kind of debatable if this is still vulnerable to cipher attacks or statistical attacks or not. Most people consider this to be incredibly difficult to break. But yeah, we can see just based upon, and this also illustrates, even modern encryption means, modern cryptographic algorithms still use exclusive OR a lot. XOR and mod are like the two main operators that they always use in these. So for example, if we have this plain text of just a sequence of bits here, we have another key. Now the key has to be the same length. This is also downside of one-time pads, but we can see, okay, we can just XOR these two things together. We get, every time it's different, it's going to be 1, so we get 1, 0, 0, 1, 1, 0, 1, 1. Great. Yeah, so we can generate pretty quickly and simply this ciphertext at a bit level. So again, you just take string, make it into ASCII bytes, and then you could apply this to it. But why? I mean, you ask, why is it one time? So if we have a key K, which is again a sequence of bytes, and these plain texts T1, T2. So if we have, there's this sort of Boolean algebra holds where if this is our encryption process here, so we're encrypting T1. If we use the same key to encrypt T2, this is going to be, and you can kind of work it out by hand, equivalent to just doing XOR together, which will reveal which bits they have in common. So let's see here. If I do my key, I'm just going to do 1, 1, 1, 0, and 0, 0. So if I do, let's see, 1, 0. So it's going to be 0, 1. On this side, I have 0, 0. This is going to be 1, 1. And if I exclusive OR them together, I get 0, 1. Right? If I do XOR down here. Oh, no, I did that backwards. 1, 0. So anyways, that will always be the case that if we get zeros, that means they're match. They're a match. So if you use the same key repeatedly, if you watch enough, you can find all the bits in common and again do another statistical attack on the encryption scheme. So you have, basically, you can only use the key once, and it's symmetric. Both people have to know about it. But it's considered to be, I'd say most people consider unbreakable. A few people think there's theoretical ways around it. It's maybe slight dissension about it might be breakable, but it's extremely hard to break. That's a big plus. It's also really simple, I could say that. This is negative key is the same length as the data. Again, you have to have the keys exchanged beforehand. But one cool thing about this is you could have, again, like a code sheet of, keys 1, 2, 3. So for the first message, you just make a couple copies of this. You give one to your buddy and you say, okay, for the first message we're going to use key 1, the second one key 2, etc. You could just have on a piece of paper. It's really simple, it's low tech, and it's very strong. So that's pretty cool, and it illustrates the use of exclusive OR, which is used a lot in other cryptographic algorithms. So one-time pad. It sometimes is still used because it's so strong. Typically, it's used in like a hybrid style system where you have another system that exchanges keys, and then this is used for all the messages in between. So let's get around that issue of the key being super long. So let's look at a way to address that. We're going to look at block ciphers. So if we take our original ciphertext T and divide it into even size blocks, so we have now n blocks. Our goal is then to encrypt each one. And again, we have to think about that style of statistical attack. So if I'm going to encrypt one block and get ciphertext out, if I'm using the same key over and over again, well, I don't want... so in one long message, if I'm using the same key on chunks of it, each block, I don't want some patterns to occur because I'm using the same key. So that's the real consideration. So there's this clever trick, and it's called chaining, where we're going to take text 1, we'll encrypt it, and then that's going to kick out ciphertext 1. Now we'll take 2, encrypt it. Okay. And that's going to kick out. Oh, just kidding. What we're going to do here, which is different, is I got too distracted by my poor penmanship. I'm going to XOR it with C1. So that's good. We're basically going to use the ciphertext here. Dash, dash, dash. Yeah, okay, I can do that here. Okay. As a way of breaking that sort of statistical connection between the ciphertext and plain text. So then when we kick out C2, C2 depends upon C1. So now that's where the chain comes in, if you will. So now I have T3. We're going to encrypt, T3 XOR C2. That's going to pump out C3. So I was actually concerned if I wasn't going to be able to do a dash line on this tablet, but look at that, getting there. All right. So now we have this way of chaining it together. Again, this defeats this sort of potential statistical attack if there's just this straight connection between the input and output. Because again, if statistics always rely upon large numbers. So if we have a long message, break into small pieces, repeatedly use the key, that might be a problem. But this obscures that sort of connection between directly input and output. Now there's a connection between the input, the previous output, and the output. If that makes sense. So this is really just simple, clever technique. Again, this encryption function could be kind of any cryptographic procedure. So this will work with, this is sort of like a meta approach. It's really sort of, it's just kind of cool when someone thinks of something so sort of elegant as a solution to a problem. So then you might wonder, well, how can I translate this into getting rich? Just kidding. This is, you heard the term blockchains. Whoa, that's a lot of highlighter. So what's that about? Well, let's say I have some record. I'm going to call it T1. I'm going to call this B1 for block 1. I'm just going to put nothing in here. I'm going to encrypt it here. And that's going to kick out some ciphertext for it. Now it could be like a hash, so it's actually much smaller than the block. That's probably what we want. So now we come along and we make another entry here. We have another set of records we want to encode, and then we throw in C1. So now when we encrypt this, we get C2 out, again with the dash line. Now when we come over here and do block 3, text 3, oh, okay, oh, wow, really saved the day on that one. Put C2 here, put this in here, and out of it's going to kick encryption process C3. So what is going on here is we're using that same chaining technique of every time we want to encrypt something, we include the previous output. So what this means is, well, let's say now this whole chain, if you will, is public. And some, naughty person comes along here and wants to change text too. Ha ha ha. The problem is C2 depends upon what both C1 and T2, and it's stored over here. So now you can verify, you can take this, apply the encryption, it should match this. And then again, if we just keep having these blocks on and on and on, that means, well, the previous C2, we need both of these things together, of course, to verify C2, but then we have C3 here. So now, our malicious person changed text 2, but that means if we take the altered text plus this C1, run that encryption process again, it doesn't match the value here. But okay, let's go change this value. Well, that's used to compute C3. And then C3 is used to compute C4. And on, and on, and on. So, essentially, as this chain grows, records back in the beginning, or in the early part of the chain, it becomes almost impossible to be able to expect you can make any alteration and no one be able to notice. So this is, what cryptocurrency is based on. This text is just a transaction record saying, I'm paying someone, so-and-so so much money, someone else, and we just have a big set of records of this. So it becomes this sort of ledger of who's paid everyone what. And then the only other thing to it is, well, you don't just want to be able to say in here like, you don't want anyone to be able to say Joe paid, Frank. You only want Joe to be able to say that. So everyone's transaction record, when you go to say, I'm going to pay someone, you digitally sign that message as well. So there's a couple layers of cryptography there. But together you end up with something that's totally public. You can distribute it. And everyone's favorite word, it's immutable or unchangeable. And you can, another way is you can guarantee its validity. Or you can say it's self-verifying, self-validity. Yeah, something like that. There's enough adjectives in there, I think you get the idea. So you can just have this totally public record of what's going on in terms of people buying and selling. And there's really no one who can mess with it. So once it's out there, it's just out there. So there's no need for like a bank, basically. And the miners are the ones who go through and verify the integrity of the chain. So they get paid in coin to do that. Bitcoin, that's how Bitcoin works. So by providing that service, you get some currency. You can then use that currency and buy, sell things. That goes in the transaction record, blah, blah, blah. So it's this really sort of clever system. Bitcoin itself, we don't know who invented it. It's this guy named Satoshi, apparently, who claims it, but it's just a pseudonym. We don't really know. Some people theorize the guy who created it is actually dead. That's kind of fun. Well, I mean, bad for that guy, but it's kind of a romantic idea of like, this guy made this crazy system that's gone. Anyways, that's how cryptography relates to cryptocurrency or blockchains. And again, blockchains can be used for anything. So this might be a good way to have, public records on, I think people should do it for voting. Hey. I think that makes a lot of sense. Or the law. So like a legal system. So anything you'd want like a good public record of, and you don't really trust anyone to maintain it, is blockchain eligible. So it's exciting technology. There's a lot of hype around it. I mean, the hype is kind of fun, but it's also sort of annoying. But it is pretty cool technology. So everything I talked about prior, we were assuming like symmetric keys. Now we're gonna get into public key cryptography. So instead of having a key that works for both encrypting and decrypting messages, we're gonna basically break our key in half. We'll have one that we can give to the public that everyone knows about, and there's this kind of secret key that's tied to it called secret key, which you'll keep hidden in private. So the idea is you give the public key to whoever, they can use that to encrypt a message, and only the holder of the secret key can decrypt the message. So this is kind of cool. The idea here is anyone can send a message, but only the receiver can decrypt. So a lot of, this is like SSL, for example, uses public key cryptography, SSH, right? This is really common. And it has this property, and this just looks maybe more confusing than it really is. If you take the plain text, encrypt it with the public key, you can decrypt it with the private key and end up back where you started. Oh, so let me draw a nice little diagram here. So you have the sender over here. They have their plain text. They're going to feed it into their public key. And then the ciphertext. So I'll have down here C is equal to FP T. So we'll send that over. And then the receiver is over here. They have their nice secret key, and they can use FS on C, and they get T out the other side. And if, some naughty person is here, so an eavesdropper is, I can put little like eyes or something. That's just, okay, never mind. Forget that art happened. If they're spying on you, if this is say if this means that the message is being communicated here in public, so yeah, we'll say public communications happening here. All they see is the ciphertext. It goes over the air, it goes over the internet. They decrypt it and be like, okay, Joe needs 500 pounds of rice. All right, send it away. Whatever the message is. So that's sort of a model. It's basically a one-way. So the idea in these sorts of systems is then everyone is a sender and a receiver, so everyone has their own public and private key pair. So then if the receiver wants to send a message back, they need to, again, set up this this whole system in reverse. Or sometimes what happens here is the sender also sends along a symmetric key to use for the receiver to respond with. So that'd be like a hybrid system. Now, digital signing is nice. Another concept here. I mentioned this with the blockchain idea. Digital signing is you're going to encrypt with you encrypt with your secret key. Then anyone can decrypt with the public. So that's a way of, you could take, your document, then through this secret key, you can produce this nice signed document here, and then anyone, that's terrible, can decrypt with the public key. So what's the advantage here? It means anyone can receive this message, so you can broadcast it, but only the sender can produce it or can encrypt. So this is the other half of like the the Bitcoin system. Is the sender would be the person wanting to give payment, for example, being like, okay, I'm going to give 0.04 Bitcoin to somebody. Or another way this is used is ensuring the integrity of downloads. So if you want your new updates for your operating system, that data is really important. You don't want someone tampering with it in transit. So the sender, your Ubuntu, Arch, whoever runs Arch, Windows, Microsoft, they have their own key for digital signing. So they sign their updates, send it to you. They can give you here the signed updates, their public key, and it should make sense when you decrypt it. Or there's variations of this, but that's the main idea. So now I'm going to walk you through an example of a particular public-private key encryption system. RSA, made by 3 guys. I forget their names off the top of my head. Kind of famous. It's a famous algorithm in the computer science world. It uses 2 properties and I've kind of covered these in previous videos. Is property 1 that's important is factoring a prime number that's a product of, or factoring a number that's a product of 2 large primes is hard, or is an NP. So if you have some number, that did not come out well. If it's prime 1, that means like it's in this sort of situation where you have some number, it's a factor of 2 primes. It's hard to figure out what those are. So that means there's a lot of candidate numbers to potentially look at, square root of n. But again, if we're talking about digits, it's going to be 2 to the d over 2 digits. So that's a lot to consider if we have numbers are huge in terms of number of digits. So that means there's only 2 numbers that are the kind of key or the way of unlocking this out of a very wide field. Shoot, I meant to highlight. You get the idea. Put the D back. There we go. The second property is determining if a number is prime is relatively easy. So I had the primality test algorithm that runs in polynomial time. So we can determine if a number is prime. And we can use these 2 things together to produce a procedure to generate public-private keys. So this is our RSA algorithm. It's very sort of simple, I guess. It just relies heavily on number theory. But let's just walk through this. So we're going to pick, I'm going to put some values over here. So the first thing is we pick 2 large prime numbers. So we can generate those. It's not too hard. This is not large, but I'm going to pick 2. Now, that's step 1. So this is, our goal here is generate public key with the corresponding secret key as well. We compute what n is. In this case, it's going to be 493. Now we come up with what r is. Compute this. This is going to end up being 448. Now we have to pick a small odd integer, e. It's relatively prime. with respect to R. So relatively prime means the only common divisor between E and R is 1. So we just pull this number sort of out of a hat and test a few. Now, we compute D as the multiplicative inverse. This is what multiplicative inverse is. So I'm going to say for this, I've randomly picked E. So there's no common divisor besides 1 between those two, E and R. Now we could play with this and see that if we set D to 269, that will work out because ED is going to be 5 times 269, which is 1345. And if we do 1345 mod R, which is 448, this actually breaks out to 3 times 448 plus 1 mod this. So we'll see that this does in fact equal 1. So once we've kind of, so you can kind of, once you've calculated that number, now we're done. So we can set P is equal to E, so and N, so it's 5 and 493, and S is going to be D, which is 269, and N 493. So we could again, so yeah, and that's it. So this is our public and private key, and then you use them with these functions. So if I took the number 327, just pick that out of a hat, nothing special about it. So 327 to the 5th power, because that's what E is, mod 493. This is going to be 259. And if we do this, if we take 259 to decrypt, now this is, the math here is a little tricky to see, but 259 raised to its 269th power mod by 493. You need to, open up Python or something like that to, oh, didn't mean to get rid of that dot. Out of this is going to pop 327. So you can believe me or not, but yeah, if you run it to like Python or Google or something, you can verify the numbers. So that, so it essentially just comes down to you just pick a few primes and then sort of calibrate these other numbers based upon those, and then you have a public and private key. So you give away P, so those two numbers, while maintaining your secret key. So this is what happens if you've ever had to generate, like for GitHub or GitLab, like an SSH key. That's exactly what's going on here. I mean, they don't use RSA, it uses something a little more advanced, but it's really this idea. So that's an overview of a lot of encryption concepts. So it covered everything from substitution ciphers, blockchains, blocking, the Enigma Machine, public-private key encryption, RSA. If you want to read about more modern, still used cryptographic methods, Blowfish is out there. It's still used. There's no known vulnerabilities for it. What's interesting is the developer, as soon as he made it, released into the public domain so anyone can use it. Then this guy went on and made something called Two Fish, because it's like Dr. Seuss, right? It's this follow-up. Then AES was developed by the U.S. government, or at least standardized by them. So this is a lot of like SSL now uses. So you can go check those out. But yeah, this is just overview of encryption. Have a nice day.